Let me give you presenter role, and you can go ahead and start your presentation.
Okay, so I don't know, at what time should I finish?
You should finish in 20 minutes, sorry.
Okay.
Feel free to just spend more time.
Okay, no, I think I can manage. I can do it. It will be a blast. But okay, so So do you see my screen?
Yes.
Okay, so let me start with the second part, the second presentation. So this training session, I will talk about cloud-based CAD parametrization for engineer design, specifically using in OpenFOAM. So I will introduce a few tools, how to do things automatically, everything based on the cloud. So, well, I already did this introduction, so I will skip this. And, well, our agenda will be this one, 5 chapters. So first, let me talk about what is parameter-based and parameter-free approaches, okay? So when we talk about parameter-based, okay, approach, it is that what we do is basic in the CAD, okay? We're working at the CAD level, we're using a CAD software. I think you have used one, or I hope you have used one. So everything you have parameters, variables, everything changes can be introduced easily, okay? So the final geometry when we have is that everything can go into manufacturer production. You have drawings, you have your bill of materials, everything, okay? Very robust. This is what we want in the industry. But the problem that we have here when we want to use this is that usually this CAD software, they are strongly coupled with a GUI. There is no way to interact using programmatic way or scripts, okay? There is no API interface, programming interface, and usually also this CAD software is based in Windows Workstation, so usually we're doing our simulations in supercomputer, high performance hardware, so it's difficult to put everything interacting. So this is what we address, okay? And I will show you how. Then the other approach is parameter free, okay? Parameter free is like working with plane. You start to push in, push out some parts of geometry. It's widely used in, let's say, animation industry, okay? So you have used Blender, you will see that that's what you do. You create cylinders, shapes, and then starting from that one, you start to push in, push out, and you can create very organic shapes, but they are not ready to go into production. This is not desirable. It's not easy to parameterize. However, if you are doing adjoint optimization, probably you are using this one when you do this mesh deformation, okay? So this kind of approaches enters in mesh deformation in adjoint, but it's tricky to use. So our approach is this one, parameter based, or we're using a CAD software. We're going to use Onshape. So basically, when you do this kind of parameterization, you assign variables, and then just by changing these variables, see that you can get different geometries, put it in your automatic loop, and get everything working. The other way is the parameter free. So here,
hear you.
Hello? Can you hear me?
Yeah, please go ahead.
Okay. So the other way is this case. So what you do here, you get the geometry, just one geometry, and then you just put points here, 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 and you just start to push in, and you see that you can get different shapes, but it's difficult to parameterize. But also, if you want to get drawings and stuff like that, it's not easy, okay? Because you have that underground parametric geometry. So that being said, that we're going to use a parameter-based approach, let's talk about the automatic loop. So the automatic loop is basically, we're going to put all these tools in action, okay? And we're going to show you an application, but this can be extended to any kind of application, so there is no limit. So basically, this automatic loop covers from solid modeling, so this is where we're going to work right now, but then we have meshing, case setup, simulation, monitoring, and post-processing. Everything is done automatically. Here's where we're going to focus. Important thing is that you need to monitor a lot of data, so don't be afraid of putting monitors when you are doing stuff and monitoring your data. Few comments on the framework is that if you are setting one, or if you want to take our approach, is that the framework, our framework is full automatic, and to some extent it's fault tolerant. That means that in case that something fails, okay, you should be able to restart. Okay, you cannot start from scratch. You should be able to restart, and you need to save everything. In cases of anomalies, also you need to detect that real time to do corrections. That's why you need to monitor a lot of stuff. Okay, and then usually always the bottleneck is the meshing, especially if you are using the tools that comes with OpenFOAM. But we're going to work with an easy geometry. It's not a problem, but be careful that as you have tricky geometry, you need to spend a lot of time to get something very robust. So this is the loop that we have. We're going to work in this geometry. So here, this is the classical case. You have flow entering here, going out here, and then entering, going out here. And we're going to change this angle, okay, to obtain here the best distribution in the outlet. So basically, we're going to do one geometry, we enter in the loop, and then from this loop that everything is controlled by Dakota, we are going to spawn different simulations, concurrency simulations, okay? Everything in the cloud. So here I'm going to run it local, but we do this usually using Amazon EC2. Then using the RESTful application, we're going to modify the parametric geometry, and then we keep going. So this is an automatic loop, how it works. So as you see, all the tools, everything is based in open source. So let's talk about a little bit the cloud-based CAD. So there are many CAD software. We're going to use Onshape. Beautiful software. I recommend you to use it. So it's a feature-based, fully parametric, it's fully professional software. Okay, it's equivalent to what you see in SolidWorks or CATIA, whatever. It's equivalent. Okay, the big advantage is that it works in the cloud. Okay, you don't need to do installation. You just need a working internet connection and a web browser, and you are ready to go. It's fully collaborative, and this is probably the most important part, that many people can work in the same document at the same time. Okay, it allows for simultaneous real-time editing. Okay, there are many features, but one is very important, is that we have access to the RESTful API. We can do programmatic design of those geometries, parametrization. So we don't need to go to that CAD interface. Okay, so we just do a web calling, and then we update the geometry. So basically, this is how it works. So here we're outside. I will show you the GUI, but here we're outside the GUI of Onshape. So basically, you have your client, you do a RESTful request. Okay, you write something, send it to the server, and then the server gives you a response. And that's all. And the beautiful here is that this can be deployed in any computer. Okay, we have done this in supercomputers here in Europe, and it's beautiful how it works. Everything. We don't need to deal anymore with that difficult part of the geometry. So basically, this is what you can do. So here I'm showing you an application, showing you the GUI. But this one, when you do it using RESTful applications, you don't see the GUI. Okay, you only will see a Python program. And you do a request, change this angle, then the server will tell you, okay, this is your geometry, you get your response, you download, and then you have your STL, and just put it in your loop and do your design optimization. Since to doing this one, geometries like this one, like for instance, you want to change flaps and slats, this is tricky to do, but since to use this cloud-based CAD, we can do stuff like this. But also remember, previously we saw overset meshes. You can deal also this kind of cases with overset meshes. So also we're putting our overset meshes in some design optimization. So now let me do the live demonstration. Okay, this is dangerous because I hope everything will work. So basically what we're going to do, we have this geometry, okay? And we're going to change this angle, okay? And then what we want to do is find the best distribution at the outlet. But the twist that we're doing here in this optimization also is that usually when you want to get best distribution, you measure something. So there are stuff like uniformity index or distortion coefficient. What we're going to do in this case is we're going to do image recognition. We design here at the outlet, we want to have this velocity distribution. Let's see what happens. So what we're doing is also co-processing. What we're running, compute here this cut plane and compare with this one. And when you get in this case it's parametric, but you can do also gradient based, then it will stop when you have the best one. But see here, by measuring this one, then we see that the best value is something like this. And see that we have very, very good distribution in this one. But actually the best one is not when you have 90 degrees, it's something between these two. So this is what we have, everything implemented. So let me open here, we go into my Linux workstation. So again, I'm sharing these cases in GitHub, so you can download everything, it's ready to run. So I will show you the first case, static measure, just the geometry. I'm not going to run this, by the way. This takes like 20 minutes using 16 processors. But first, let me show you, this is Onshape, okay? Also, I'm sharing these geometries if you want to reproduce what we're doing. And I will go into this case. So see that we have the geometry, everything is conveniently parameterized, and see that if I change this angle, let's put here 150, everything will be updated automatically. So what we're going to do, change this, okay, but we're going to do it in a programmatic way. We are not going to deal with the GUI. So you have the script, you download the public API on Onshape, you have the links in the presentation as well, and you will get this script, stuff like this, like you need to put your credentials, so you will have this file here, you put your credentials, you need to generate it, okay, and then you will have a script. This is a script that is doing everything automatically, okay, so this is in Python, okay, I'm calling some functions, updating everything. So let's run this one, let's see what happens. So I will go here, by the way, I'm using Dakota, everything is managed automatically by Dakota. Okay, so if I go here, Dakota minus, we're going to just generate the geometry. So if I go here, see that it's running here in a programmatic way, it's doing the calling, but then see how it's updating everything. So this is the power. And by the way, remember that I told you that this is fully collaborative. You can have many people working in the same document, and you can parameterize many variables. So in this case, just the angle, you can change diameter, everything that you put here in your feature history, you can do it. So basically what you are doing is generating each geometry in each work directory, and then if you have your optimization loop, you just do geometry sampling and everything, okay? So this one you can see real time. We will run in a sequential way, but then there is another way to do things more efficient. So I will go into second folder, okay? And this is how I recommend you to do things, using this approach. So we have a second geometry here, using configurations. So you have here OPT conf, and see here that all the parameterizations, now we have it here, okay? So this is much better because this will let you do multiple callings at the same time. Previously, you are just able to do one call. Here you can do 10 or 100 calls at the same time and download everything simultaneously at the same time. So see here that we have 3 variables, we access these 3 variables, and then we get everything. So here you will see that we're running in parallel. So if I go here, you see 4 directories at the same time. It will call the geometries, you get everything, and then we know already the workflow. So everything you put it into your directory, see that it's already done, 5 geometries. You have the STL here, and then you just can put that together to run the case. So just to show you now how to run the case, okay? So if I go here, static mixer 3. So here that we set up everything. So before doing this one, you need to plan your case. So we already know how it works the CAD. So you see here that I have a case base. This is my OpenFOAM case that I already predefined, preset up, that it can run. It runs really well. So I have it here, and what it will do that each time I create a new of those folder, copy this one, and start to do all those operations, how I'd say here in the simulator script. Okay, so see here that it's doing everything, calling on my script. So this is the way like you traditionally run an OpenFOAM case, but everything is being managed automatically by Dakota. Okay, so that is how you set up. This is fully working. Okay, so let me show you, for instance, just to launch it, you will see that since how would do. Okay, I'm almost done. So if you launch here, you see that it will create one directory. you have the geometry, STL, and then it will start to do the operations, and see that it will start to run snappy, everything sequentially as you do it, okay? So the thing is that you just need to plan, you know how to communicate with your CAD, Cloud-Basic CAD, everything is ready to go. So the final part about this one also, you will have here the script to do the image recognition. I will show you how it's running, but here what we're using, it is the structural similarity of images. So basically we have this small script and it will compare images, okay? So we have used more complex way, but I think sometimes the beauty is simplicity. So as you go here, I will show you what is going on. Python. So what is happening here is that it will start to open files and see that this is my target, this is what I have. And it's giving you this index. The closer this index is to 1, the closer it is to your target. So basically what you're doing is this one. Each iteration, keep comparing, keep comparing, keep comparing. Okay? And probably this is the best one. You see you have the largest. And that's all. So these are the outputs of that case that you run. You just put it here. So what you do now is just put everything together and you are ready to go. So just to finish, okay, so this is what we did. So main takeaway. So basically, thanks to the use of this cloud-basic approach, we were able to eliminate all these problems that we usually have, that we cannot do, we cannot install the software in the supercomputer, or how to communicate with different systems. Everything thanks to using a cloud-based CAD application, okay, which also lets you do collaboration. But what is important when you are doing an engineering design loop, that this is a meticulous and thoughtful process that requires planning. You need to plan everything before doing, okay? Also validate and calibrate your design loops. Be sure that everything is working, and also very important, it is fault tolerant, and monitor your data real time, okay? So as you can see, open source technologies mature enough to tackle industrial applications. We have used it for complex programs, and the cloud is here to stay. Just to net out, something that we keep also in our vision is this here. If you haven't read this report, just read it. It's a beautiful one. But see here that we're trying to address everything. Like a single engineer needs to do large simulations, a parametrical study in critical time periods, needs to manage everything, needs to monitor information, needs to use machine learning, needs to use all kind of techniques while doing this design optimization. So we're trying to address everything that is stated here. Just to end up, here in this link, you can download everything. So we put everything in GitHub, also in Onshape. You can get access to the same documents. Okay, and well, I think I am on time. Thank you very much for your attention. And if you have any questions, just let me know.
Thank you, Joel. Anyone has a question? Yes.
I have a question. I mean, this is amazing, the fact that you strung together all these different services to put together parametrization. I'm wondering, how long did it take you to set this one case up?
Actually, everything depends on the resources you have, but this case is you have, let me show you something here that we have. You see here that here we run with 3 design variables. Okay, so here we have a parallel coordinate. These are about 150 simulations. To get this, it takes in a computer with 32 processors, which is something that you can find today. It takes about 3 hours, okay? So you do concurrent tasks, everything. So as you see, it's very affordable, okay? You have the resources, be careful, plan everything and distribute. For instance, we have used 1,000 processors, using 1,000 processors in 24 hours, meshes that are about 2 or 3 million cells, relatively large, we can get about 3,000 simulations in 24 hours. A lot of data, okay? So it's very affordable.
And have you looked at Fusion 360?
Fusion is beautiful, but the problem is that you don't have the programmatic API. The only CAD software so far that you have access to this programmatic API is Onshape. But yeah, Fusion is beautiful.
Yeah. Any other questions? All right. Thank you very much, Joel.
Okay.
And
You're welcome.
thank you remotely.
Yeah.
Okay, you have a good rest of your day or night.
Yeah. You're set 7. So I'm putting everything online so you can get everything. If you want, I can send you the link. So everything is working. You can try to reproduce everything. So thank you. And well.
Yeah, thank you. All right. Well, bye-bye now.
Okay, bye.
Bye.